Yeah, good day. This is a recording of the whole process of leading to the prediction of failure rates using artificial neural network. Now, in a prediction, in the prediction of any data set, there is a cycle it goes through. It starts from the very first, which is the data wrangling, which involves data cleaning and data manipulation, then the data preprocessing, then the feature selection, then the feature engineering, then you go to steps such as the model selection, the model training, the training of the data sets on the model, and then the model evaluation and model testing. In this case, this imports pandas as PD, imports numpy as NP. This first block of code, they are libraries which we'll be using for our analysis and prediction. Pandas, they are used for data analysis. NumPy, it's used for numerical analysis, numerical Python. Seaborn is used for statistical visualization or statistical plots of the data set. Matplotlib, which are presented as PLT, are used for normal data visualization. Now, there are two data sets present here. The first one, I named it data, and the second one is data 2. Now, I'm using pandas, which are represented as PD here, to read CSV. You read CSV, which is a function to read the two data sets. Now, this data.head simply implies the head of the data, first 5 rows, 0, 1, 2, 3, 4, which is 5. Computer starts counting from 0, and these are the columns there: the date time, the date/time, the drive frequency, the intake pressure, the intake temperature, the motor temperature, the discharge pressure, and so on. Now, this is for the head. Now, this is the tail. That means the last 5 of the data set. So the data set is all 406. Now this is it. Now for the data shape, it's 407 rows and 10 columns. So we have 407 rows and 10 columns. We have to take it this way. If we have 406 or 407 rows and 10 columns, it is not enough for prediction. It is not even enough for analysis. But we are still under the development, the data manipulation, and also we are still clearing the data set. Now this is the data.info. This is just to show information about the data. The D type, which is this is object, simply means like it's a string, right? Date type is still an object. This one is a float. That means it's in decimal places, and this is an integer. So basically, now for the data too, the same process, the first 5. Now we can see then the data.tail. Now this shape 15,115. This is enough for prediction. Very enough for prediction. This is the information about the data set. Now the data time. What I simply did here was splitting up the data and a bit of feature engineering. We call it feature engineering in the sense that I wanted to have a column that has just time, a column for time, and a column for date. To do that for the two data sets available, for data, I did data.time is equals to data, the date time, which is the a colon here, and this is the whole data set, the colon, this one, dot apply lambda. This lambda x is just simply representing x to split, split this. I'm splitting it. The date time, I'm splitting this, I'm splitting the 1 and then the 0. You understand? Now, if I'm splitting it, I'm using this split as a way to separate the date and the time. Now it's together here. Now I'm separating the date and time. Why am I doing this? Now if you see between this 9/10/2024 and then the 1150, there's a space here. Now the space is what I'm using. That's what I'm using to split it. That's why I put a space in between these columns that I used here. Now one represents, one is computer has 0 and 1. One is here. This is 0 and this is 1. So just like here, this will represent 0, the date represents 0, the time represents 1. So for the time is 1 and for this date is 0. Now me now dropping this time column. I'm dropping it because it will not be needed again. I will have, just like here, I will have my time and my date columns. Now I did the same for the data2 data set also. I dropped it and this is the result. Now this particular program in this code 20, this is used to swap, interchange the places of columns in a data set or in a data frame. Now here's it. I have my drive frequency here, but I want my date and time to come first because it is easier that way to say, okay, at this date or at this time, this is the intake pressure. It is easier and it is also faster when you want to start plotting the graphs for data visualization. So this here, columns is equals to, I presented this, executing this code for data, right? And then I did data.15. Now I have my date time here for my data. Now for my data too, I did the same thing, just the same process. Now I have my date time here for this. Now me doing the still getting the info to check if our data set is still intact, which is still intact. Now this next step is not.sum. This is not simply checks for if this data set contains any null values. Now as you can see, the column date contains 0 null value, time 0 null value, it's all 0 or true. For data 2 is also all 0 or true. Now another thing to check for, there are things to check for. To check for is not if there's a null value. If there's a null value, you remove it because you can't predict with a null values. With a non-value rather. But data 2, for this one, the data duplicated, we also go for the duplicates. If you have lots of duplicates, you can't predict with that too. Because it's like saying you are predicting with a column that says 2, 2, 2, 2, 2, 2, 2, 2, 2 or 0, 0, 0, 0, 0. It's not, you can't predict on that. If you want to predict on that, it's going to be 0. There is no prediction, right? So when you do something like that, this is duplicated for data. I checked data.duplicated or sum. There are 392 duplicated or duplicates in it. So if you have 992 duplicates, I checked for the data too. It is 0. Now bear it in mind, the shape of data is 407. The shape of data 2 is 15,115. Now even at this 407, we still have 392 duplicates, which can be said that it is not, when you decide to drop the duplicate like I did here, data is equals to data dot drop duplicate here. When I did drop the duplicate and for data 2, now for the data dot shape, when after I drop the duplicate, I have 15 data sets left. 15 rows. You can't even use that one to predict. 15. It's not, you can use it to predict, let alone fitting it in a neural network, using it for deep learning. While for data 2, it has no duplicates. It's still 15,115 with 11 columns. It is now okay. 11 columns because I've splitted the date time. It was 10 before, now I've split the date time, is now 11 columns. Now data 2.8. Now since this 15, we can't use this 15. We decide to not use it. We go on with the data 2 because it is not usable. With the data 2, we can use to predict. Now for the data 2, the data, I also did the data, converting the date to date time. There's this particular function, we use pandas for it. To data, pandas to date time simply is saying we are selecting this date here that we have here, this column here, the head of it. We are setting the day first as true, in which the day first will come, the format as mixed, and the errors as chorus, which means it doesn't go over it. If there's an error, it wouldn't print it out. That's the first for chorus. I did it for data and data too. Still putting the data.info and stuff. Now you can see data.info. This has changed from object to date time, just like we converted it to date time here. Likewise for this same thing here. Now we can see it here. The format has changed. This was the previous format, 8/20/2024. Now we have 2024/10/9 for data, and then this one 2024 8/20. So the format has changed. That's basically what we did. Now value count is just checking the amount of the value of everything there. Now this is a continuous kind of data set. It is we use it, this kind of data set is like a continuous stuff. So it's basically used for regression analysis. When you do this kind of data set, you have 8,971 zeros here, 0.0. We have 3,681 35.11.1 discharge pressure. The amount of times this is repeated, and it can be seen in the data set. When you check the discharge pressure, you have 000 here. Here we have 35.111. So this 35.111 is repeated 3,681 times. This 000 that we have here is repeated. This is still for data 2, so it's just the head and the tail. It's repeated for 8,971 times. So that's just the purpose of value count. It will tell you how many times this is repeated, and then the others they're repeated 111, and that's it. So for the data differential pressure, now this is NumPy. It's used for numerical analysis, numerical Python, in the sense that I'm looking NP is used to calculate numerics, it's for numbers. Now when you do that, the NP.absolute, meaning I'm changing all the values, whether negative or positive. I'm changing everything to be positive. I'm constraining everything to be positive. Now doing that requires finding the difference. The differential pressure is the difference between the intake pressure and the discharge pressure. Now this is all I've done here, doing it for data and then for data 2, just like I've done here. Now you have the np.absolute this and this. Now this is it. Now we have our differential pressure here. As seen here, this is our differential pressure. Now there's a way we now do a grand scale of feature engineering. I'm now selecting these numerical columns here now. Intake pressure, motor temperature. I'm taking it as numerical pressure because this date and time, they are not numerical numbers. They are not numerical. They are date time. Now that's why I named them time columns. Now this is intake temperature. I put everything here and I put everything here. Now if I want to plot a data set from that, me here, what I'm doing here is I'm doing just basic intake pressure versus time, in which it bring out the date. We'll go to that. So this here is just numerical columns. This is just time columns. Now PLT, I'm said is used for. I've said earlier is used for data visualization. Now I'm setting the fixed size, so the thing, the graph, the plot is, you can see it very well. And then I'm plotting the date on the x-axis and the intake pressure on the y-axis. This is a line plot. I'm setting the color to be cyan. The title will be intake pressure versus time, as displayed here. The X label will be here. The Y label will be intake pressure. Then I'm saving it. I'm saving this figure as intake pressure versus time graph. Like I will be showing, I've showed it in the report. This is just an explanation. Now PLT does show. It's just going to be short. Just show the data. Now that's what we have here. From 2024, January 2024 to the October 2024 rather. This is how the intake pressure has trended against the year or the month. This is it. This is the visualization of it. Simple as this. Likewise, the same thing for the intake temperature. This is how it has gone. Just the same process. This also for the differential pressure I just plotted. This is how it has gone. Then for the motor temperature, this is how it has gone. Just the same logic, the same process. Now this is an analysis of variance. In the sense that me saying PLT.figure, I've explained this earlier, this SNS is seaborne, like I said earlier in the very first block of code. SNS is used for statistical plot. Now, if you want to use SNS, is a seaborne statistical plot. Now, box plot is basically plotting the upper bound, the lower bound, and the quartile range and everything. I'm plotting everything using a box plot. This is how a box plot is. Look at this drive frequency, it shows it better. Now, this is the upper bound, this is the third quartile, this is the first quartile, and then there's a lower band under it. The lower band is just almost the same thing with the first quartile. Now when you look at this box plot, basically is plotting the mean. It will tell you, you can use box plot to get the average of a particular data set or a particular column in data set. Like here, it's used to show the mean, and where the mean is, where most values are concentrated on. You can use box plot to get it, and then the variance also. So that's why it's used for analysis of variance, ANOVA, and then just statistical description of the data set. So basically, I'm doing it for the data and then from the data too. As you can see for the data too, you see. Now, when I said what we check for to clean the data, we are still under the process of data wrangling. We've done data cleaning. Now, what we are doing here is we are checking for outliers. There are things called outliers in when you are doing analysis like this. Outliers are basically if you have a class of group of students that are 12 years old, the average age in that class is 12, and you have a child that is 16 years old. He is an outlier because it does not, with age, when you look at the class with relative to age, it does not belong in that class. That is the basic stuff of, that's the basic meaning of outlier. Something that does not belong, that is more than the range, right? So now here you have, you see, there are no, this is still very normal, this is normal, this is normal, the digital pressure is normal, this is still normal, this vibration, one vibration x is normal, but this PT, you can see that they are like data sets on top of the upper bound and then the lower bound. This intake pressure is normal. Drive frequency also has an upper bound outlier. This differential pressure has lots of outliers. Lots of outliers are seen here. It has lots of outliers because it is, as you can see, the lot of outliers here is like on the upper bound. You have lots of outliers above the upper bound. What we do here is we correct those outliers. That's what we do. Now, correcting the outliers simply means there are two ways you can correct an outlier. It's either you submit. I'll show you the way we did it here. Now, this correlation here is just basically saying for numerical columns. Remember when I created it into a numerical column, like just here. I didn't. Yeah, this is numerical columns. The columns included here, I just intake the numerical ones. I'm not including the time columns. So when I'm doing that, I'm basically saying the correlation of numerical columns. That's why you have the intake pressure, temperature, the motor temperature, discharge pressure, two currents, vibration Y and vibration X, PT, intake pressure, drive frequency, and then differential pressure. Now, me basically finding correlation is just finding the correlation, how correlated a data set is to it, how connected a colon is to a colon in the data set. Now, here you can see intake temperature would be correlated, would be 1, it is 1/1. It is 100% correlated to intake temperature, just like here, you see, intake temperature. But intake temperature to motor temperature is 0.999 correlated. Can you see? It's very correlated, but it's still 0.999, not close to 1. Like for discharge pressure, like for two currents, vibration Y, vibration X, PT. Likewise, PT is negatively correlated. Now, this vibration Y is averagely correlated, but this is low, very low. It's not that correlated. This is even lower because it's on negative and it's very small. Negative correlation also works. Negative correlation is like saying it also has a very huge impact on a particular column. So when you have a negative, we'll get to that part of correlation. I will explain better when we get down. Now, these are just the correlation. Likewise, for motor temperature, you can do that, check everything to just check the correlation. These are statistical, to get the statistical description of the data set, to be familiar with our data set. Now, for the description, see, this for describe is also for statistical description. Now, I'm getting the count on intake temperature, the mean of the intake temperature, the standard deviation of the intake temperature, the minimum value of the intake temperature, the 25 percentile of the intake temperature, the 50 percentile of the intake temperature, the 75th percentile of the intake temperature, and the max value of the intake temperature. Now, I'm doing that for everything. See, numerical columns, in the numerical columns, I'm doing that for everything. This is just statistical description. Now, handling outliers, like we were doing before. Now, this handling outliers, like I was explaining before, what I basically did here was I used the interquartile range method. There are two methods. There's the use of the z-score method and then the interquartile range. But the z-score method removes from our data set. But this just equates, it aggregates the data set. Now, let me explain better. This Q1 is equals to data 2. I'm using data 2 like I said because the data, we can't use it as just 15 rows. We can't even do any analysis on it. But with this, we can do lots of analysis. Now, because it's 15, above 15,000, above 5,000 data sets, so we can do analysis with that. We can even fit it with prediction on artificial neural network. Now, this Q1 is equals to data 2. I'm doing for PT, like same here. PT has the outliers, drive frequency, and differential pressure. All I'm doing here is I'm calculating the Q1, which is the quantile 0.25, which is the 25th percentile, and then the Q3, which is the 75th percentile. I'm now saying IQR is equals to interquartile range is equals to Q3 minus Q1. What I get here and what I get here in the PT minus Q1, then LB, lower bound. Lower bound is equals to Q1 minus 1.5 times IQR, which is a given formula. It is a formula, a statistical formula. It is a correlation derived by bodies of a statistical person. This is what we use in Python. Now I'm getting the LB and I'm getting the UB, the lower bound and the upper bound. For PT, this is it, 275.45 and 317.45. This is the lower bound and this is the upper bound. So for likewise for the drive frequency, the same thing is done, and then for the differential pressure, the same thing is done. Now for the what I'm not doing is I'm not saying in data 2 you should locate. This is data set, data 2. You should now locate, this lock is locate data 2, this PT, locate this column. Any in this column, locate which is greater than the upper bound. Like it's still in PT. This still represented that is in PT in this data 2. Now equate it to upper bound. I'll go again. This data 2 is the way we write code in Python. Data2.log in data 2, locate this particular row. This data 2 plus is is in the PT row. This data 2 into square bracket PT colon is saying in this row, anything greater than that in PT, in that same PT, equate it to UB. So, like here now, this PT now, everything that is up here, upper side of it, this upper side, anything that is in the upper side, it should equate it to the bound, to the upper bound. Now this is the upper bound. This line on top is the upper bound. We can't really see it here because it's very fused in together. But she equated to the upper bound. Likewise, I did the same thing for the lower bound too. See, likewise for the lower bound too, you should do the same thing. Anything less than the lower bound, because lower bound is down. Anything that is less, which is down here, you should also equate it to the lower bound. That's just what I did for the PT, the drive frequency, and the differential pressure. Now to check if my analysis, what I just did, if the operation I just carried out has worked. To do this, all I have to do is now plot the same thing I plotted here, but this time I'm now saving it because I want to save it so we can see that I've done the analysis. I'm now saving it using save pig. I'm adding a title to it. That's all I'm doing. The other one we didn't include this three. Now SNS.boxplot, this is it. That are two numerical columns. Now I'm plotting the numerical columns here, just like I did here. Just like I did here. And I'm saving it here. So now you can see it's different. That frequency is still is normal now, but the differential pressure is also normal. Can you see it has been equated to the upper bound? You see, they are no more, it's no more as like this, it's not like this again. It has changed. It's not like this again, it is now like this. Now that's basically what we just did. Now I did the info to check if our data set is still intact. We still have 15,115 rows still intact, and then we have float, which is the data type is float, decimal places. Now for the value count, I did value count again. Now for this value count, I'll come back to this for the value count. The value count here, we have 0.00 ranging up to like 14,277. This is not good for analysis. Why? Because if you have a particular value that is 14.2, that's like I said before, you have 0.0000 up to 14,000, up to more than, even almost up to more than 80% of the data sets. That particular column is not good when you are selecting columns, features that you can use to make prediction. You can use it to make analysis, just like I've done here in this box plot, but you can't use it for prediction. And now we are heading towards prediction. So just like I did, and also the PT also, when you look at the PT, a particular value 43.225 is what is repeated for everything. This is not good for a data set. This is not good for prediction. We can't use it. So those are the two that I noticed we are going to be dropping. Now that's what I did. I dropped those columns, PT, and then drive frequency in our data too. Now statistical description, further, numerical frequency distribution. When you talk about numerical frequency distribution, this is basically plotting. Distribution has to do with histograms. We are plotting histogram, but we are making it a statistical histogram, not just PLT, not just matplot, not just data visualization. We are statistically plotting the graph in so as much it can give us a better understanding of our data set. Now, when you do numerical frequency distribution, there's something called frequency distribution. You can have a skewed frequency distribution, or you can have a normal frequency distribution. Now, when you have a normal distribution, the mean, the average values tend to focus on the middle. You have a bell shape. This is the KDE, the kernel density exponential. When you have this KDE that is centered around the middle, when the bell curve, you see this bell curve that goes like this, when it's centered around the middle, that means your data set is normally distributed. But when it is focused like here, around the center here, around the edges here, it is a skewed frequency distribution. That's just it. Now here you can say it is kind of a normal distribution. We can still call this differential pressure a normal distribution, but this is a skewed one. Likewise, this is not very concentrated around the middle. Now, this is just what we did for it. I did a subplot to plot the pressure, the ones with the pressure for discharge pressure, intake pressure, and then differential pressure. I'm plotting it at the same side, the pressure ones. So all I did was PLT those subplots. I'm using a subplot, 3 of them. That's why we have 3 in the middle. I'm putting one here. I'm putting the discharge pressure on one, on here, the intake pressure on 2, and then the differential pressure on 3. Now doing that, I'm using the x is equals to discharge pressure, plotting from the data 2, and then the KD to be true, as that's which I want to show. I'm using blue as the color here, magenta as the color here, and then cyan. So basically doing that, and then I'm saving the figure such as frequency division of pressure features, like I said, of pressure features. That's what I used to save it. Is there. So likewise I did for the temperature also. You can see the distribution of it. This is skewed. It's around the edges. It's not concentrated around the center, which is 60 here. Likewise here. That's just to show we are now understanding our data sets better now. We are knowing it is skewed towards the beginning and the end, not towards the center. Not towards the center, in which the center would be the median, and then the mean, which is concentrated around the center. That's just it. So now we are going to, so like I said, this is just statistical division, numerical distribution. Now we are going to this. Now what I just did here was, now we are looking for, I was given this information on the data set that now if I want to, for those columns that have zeros, because we have a lot of columns that have zeros, 0.0, that's to show that if let's say the 2 current now, it is 0 or less than 0, that means the data, the ESP, the electrical submersible pump, has failed. If you have a 0 value, that means it didn't work. It didn't put any output, or it didn't get charged. That means it didn't work. There's a failure. So as long I now said this, they're in Python. There are 2 types of functions. There's the inbuilt and there's the one you create yourself. Now this is an inbuilt. This is what I created myself. Sorry. I created this. Now I'm saying define. This def is used for function to create a function. Detect anomalies in rows. Now this row is just a parameter I just decided to put. I can put any value there, but I'm trying to use row because it's row I want to use. I'm just trying to use it. It's just cliche, just using the row. Now if I'm not saying anomalies should be in a list bracket, a square bracket. I'm not saying if row into a this bracket of intake pressure is less than if in any row. If in any row, just like so that you understand better. If in any row the intake temperature is less than or equals to 0, the anomalies, this list, it should append no intake. That means no intake temperature, no intake. That means if it's less than or equals to 0. I did the same thing for tool in a row. If the tool is less than or equals to 0, the same thing for motor temperature, the same thing, I'm appending it, the same thing for intake temperature, the same thing for vibration X and vibration Y. I use and because I just wanted to shorten the line of code. This if chooses this one, the discharge pressure also, and then the differential pressure, I used it for this. Now I'm saying it to append the failure statement I want you to make. Now what I did here is now I now return see return comma in this row. It should return comma. It should join the comma. If let's say like here now, if we have a row in which the intake temperature is 0 and then the two current is 0, it should print out no intake and then comma no current also. So in that way, I'm saying it to join the anomalies. If there is a case of an anomaly, that means if there's an anomaly, that means if a particular colon has 0 value, or less than 0, if anomalies, it should join the anomalies. If anomalies, it should join it. It should print out, it should join the anomalies. Else, that means if it's no anomaly, if there's no anomaly, if there's no 0.0 value or less than 0.0, it should print out normal. So that's basically what I did here. I'm joining the anomalies if there are more than one colon in a particular row that has fault. But then, if there's one row, like here now, the row here, can you see there's nothing like 0 here in these numerical columns now. This doesn't have 0, this doesn't have 0. There are values here, even if it's very minimal, there are values here. It's greater than 0. It should print out normal. Else, that's the else condition. If anomalies, it should print out this, but else, normal. I can decide to write it separately, but it's a line that I can join together. Else, you should print out normal. Now, what I now did is I applied detection function to each row. Now, what I did was I now decided to do feature engineering. I created another column, which is the anomaly flags. I created another column. I'm not saying it should now apply what I've done here, like I've done here. It should now apply all this block of code into. It should apply it to data 2 for this feature engineering. It should apply it here. And on this column, this axis 1 means axis 1, it should be on the column side, not on the row. So now me doing this, it will now bring out, you see, everything here, because they have values, it has normal. But if you look at the tail here, because this one has 0, this one has 0, it has joined it. Can you see? It has joined it, telling me no intake, no current, no temperature, just like I said here, just like I explained here exactly. For the tail, that means for the tail that has 0, 0, 0, 0, 0, this is the last 15, and this is the first 15. Now basically saying that I can now say the anomaly flag here, there is a failure. Even if it's just one, and if it's not that it's combined, if it's just no intake or no current or low motor temperature or pump starvation, even if it's just one, it should print it out as failure. Because if there's no intake pressure, well, it has failed. If there's no two current, it has failed. If there's no intake temperature, it has failed. If there's no discharge pressure, it has failed. So even if one column has 0.0, it will fail. The ESP will fail. There will be an anomaly flag. That's basically what I did here. We are getting there. Now I now wrote another code in such a way that now we are looking for a no or yes. It is easier, instead of, we can't make prediction based on no intake, no current. That's too cumbersome. To get it, that means if it has, even as long as, say, what I now did here was I now created a new function, failure label. Now this failure label should represent in data 2. Obviously in data 2, I'm using data 2 now because I'm using the data frame. Now if data 2 anomaly flag is equals to normal, if any row in data 2 is equals to normal, as long as it sees normal, it should represent it as return no. That means no failure, because I'm making this place failure label. That means no failure. If there is no failure, else, if anything other than normal, if it's just no vibration or no moment, or is this combining it, I appending everything together, you should print out yes that there's failure. Since if there is one, there's failure. Now let alone of having multiple, like no intake, no current, low temperature, then you should print failure. Yes, which is yes.
Now I'm doing feature engineering, creating another column to say if it's normal, you should print no. If it has even as much as just no intake, you should print out yes. I've applied it just like I applied the other one. I've applied this column now. Another feature engineering. Now you have 12 columns now. Date, time, intake, temperature, intake temperature, motor pressure, up until the anomaly flag and then the failure label. Now with this, we can now do the failure label. The amount of yes that it failed is 8,192. The amount of no that it didn't fail is 6,123, just as seen here. Now for the value count of the anomaly flags, you have the one that has no intake, no current, low motor temperature, no vibration, no discharge, no flow. We have 8,171 that says so. For normal, we have 6,123. Well, normal we say no. But this one now, we have the one that has just no vibration, just to show that we have some columns that some of these are not entirely zero. That's why we just have no vibration. Maybe that would be in the vibration Y and vibration X, which are set as no vibration, just as seen here. See, no vibration to be in this vibration X and vibration Y, no vibration, just as seen here. So we can go here and say, okay, this is the value count, just to get a bit understanding or more understanding of our data set. Now I'm dropping this anomaly flag because we've gotten what we needed from the anomaly flag. We've gotten the failure label that we need to make prediction. So the anomaly flag, we don't really need it. That's why I dropped it, and then we now have, I now named it as DF is equals to drop. I'm naming our data set, our data 2 now, I'm renaming it as DF, which means data frame, as this. Now we have this df.head, now we have it here. I've removed that one, so we have failure label alone. So failure label, no, this means it didn't fail. No, it didn't fail. Yes, that would mean it failed. I just printed the head here. Now for the data, just like I printed before, yes, it's still the same, it's within the same process. Now unique is to check the amount of, it's a binary kind of stuff. Is it a yes or no? It's a binary type of data set. It's a binary type of data set. So it's a supervised learning type of type of operation we are going to create. Kind of prediction is supervised learning, and we use is either classification or regression. In this case, it's a binary classification, just to, if it didn't fail, then that's no. If it fails, then that's yes. So that means no or yes for unique. For n unique is the number of the class that is there. That means no and yes is just 2. Now df does is not just to check to be sure, it's still 0, 0, 0. Duplicated sum is still 0, 0. So we are very sure now. Statistical distribution of our preprocessed data. Since we are now starting to preprocess data, we've done some feature engineering, so I'm still doing the statistical division. Now what I did here is I'm doing df, which is what? Just this df is just our data 2 absent the anomaly flag. That's just our df, just like because we've dropped it here, we are equating to df. Now what I did here is I now said df dot group by failure label. Group by failure label. What we have in failure label is just no and yes. The discharge pressure, the mean, the average value of the discharge pressure, we are grouping it by the failure label. So the average value of yes, this ray, I'm using ray to equate it. Now ray dot plot, I'm plotting the kind of it to be bar. This is bar, it means bar chart. Now for better, this is just visualization. You can be like, oh, I'm still confused, but let's go further. This particular row, particular block of code, this cell here, explain this such that no, we have 3,712. Yes, we have 8.4. So that's why you cannot see it here. You see, even from here to here is 0 to 500. Yes is 8. This is 3,000, more than 3,005. So you can see it here. That's exactly, and now I did the same thing for differential pressure. I did the same thing for intake pressure, and that's it. So that's just the basic explanation of it. Now this is the measure of data variability. What do I mean by measure of data variability? It's simply saying the box plot, just like I said, is just another analysis of variance. The box plot that we've done before, just like earlier, for DF, you see, it's still very normal. There are no outliers. It's still very good. We can predict with it. Now we are moving to data processing, analysis, and prediction. Now, data processing, preprocessing. What we mean by preprocessing? Everything here. If you check the data.info, like I've done, the data.info simply says everything is float. We can work with numbers. We can work with numbers, but this failure label now, this failure label like we have here, is no. We can't work with no. No is not a number. It's a string, as we are concerned. It's a string. Now if we work with this, now we have to encode that particular column. We encode it such that maybe no will represent 0 and yes will represent 1. That way, it's numbers now. We can work with numbers. So that way, we are just doing from sklearn for preprocessing import label encoder. This is just a module for encoding in Python. Now I'm using df.failure label, that particular column, the failure label column. That's what I'm doing. The failure label column is equals to label.fit transform. I'm now fitting this label, which is the encoder. I'm fitting and transforming this particular column. So now we don't have yes or no again. No now represents 0. Now if you can see here, the no here is no is what is here, data.df.head. No. Now we are representing, that means our no has changed to 0, then our yes has changed to 1. Can you see? Just like we have before. If we check the yes here, yes is 8,992, no is 6,123. Now here, our 1 is now 8,992, which means that 1 is representing our yes and 0 is representing our no. That's just simple. Now this is just me creating, just like I did for numerical columns, and I'm putting predictable, in which the columns that I think I can predict with. The columns that I can't predict with date and time. No, these are columns we can't, there's nothing, date and time is not contributing to failure. Intake temperature, these are the parameters that are contributing to failure. Now me doing that, I'm not doing the describing, just to get the description of data, the mean, the standard deviation, the minimum value, the 25%. I'm doing everything. Now the df.predictable.correlation, I'm not putting the correlation, I'm looking for the correlation with failure label. If you decide earlier, I just did the correlation. Now I'm looking at the correlation with failure label. Now the correlation with failure label is basically saying, you have minus 0.9996. That means intake temperature is negatively correlated with failure label. I'm choosing failure label for the correlation. Now, if it's negatively correlated, that means maybe a decrease, like the condition I put in before is that if it is 0 or less than 0, that means a decrease in intake temperature will mean an increase in failure. That means maybe it will print out yes. That means if you don't have enough intake temperature, or if you have maybe high intake temperature, maybe you have low intake temperature or high intake temperature, it will print out failure. You have to have a moderate one that will keep the ESP going, because if the ESP gets too hot, the intake temperature, it could cause failure. It could cause maybe it will not discharge again. Likewise, the motor temperature has a negative correlation with it, like you can see. So that means it is inversely proportional to each other. That means if one increases, one decreases. Or if one works, if one is very high, the other will be very low. That's just it. Now failure label obviously is going to be 1, correlated with each other as 1. So everything is almost negatively correlated with it. That means with increment in this, there's a failure. Like it's normal. If you have a particular column, like these columns now, 2 current, if your 2 current is low, then there is failure rate. And with this data set, we can see that it's tending towards the lower part, because these pressures are moderate. But when you look at when something is 0, obviously it's failure, and we have lots of zeros here. So that means they are failures. So like I said, that means they will be negatively correlated with it. Now this is just me doing an analysis in heat map. This is SNS, like I said, statistical visualization. Heat map, I'm not creating an heat map for the predictable column that I created. This predictable, I'm not putting it in a data frame. Dot correlation, I'm plotting this correlation. I'm not putting failure label, I'm putting correlation to each other. I'm putting my annotation to be true, and then the C map, which is the color, as varieties. Now this varieties is simply going to tell you, okay, this is going from this to this. Now we're now doing it. I'm saying, okay, the title, I'm naming the title data correlation. I'm saving it as data correlation also. Now when you see that, when you see this particular image here, this diagram, you'll be like, okay, what does this say? Now if you check, I'm trying to check the correlation of those data, like I printed here, to failure label. Now saying intake temperature to failure label, it has rounded it up, minus 0.999, it has been up to minus 1. It's negatively correlated with this, highly negative correlated with this. That means it's very important to it. That means if something is happening with the intake temperature, it affects this in the opposite manner. Likewise, the motor temperature in the opposite manner, because it's negatively correlated. Likewise, this and it is minus 1. When something is, when they say correlation between feature A or A and B is 1, that means A and B is, if it is 1, that means it is directly proportional. That means it is very highly correlated. You can't have a correlation of 2. Correlation is based on percentage, and when you have a correlation of 100%, 100% is the same thing as 1, right? That means the same thing as 1. But when you have of 0.99, that's like 99%. It's also very high. But when you have minus 0.52, it's still very low. You can check but minus 0.52 is higher than minus 1. But this doesn't mean, this is just saying it is highly negatively correlated. But this is low negatively correlated. So it's not as correlated as these ones that are purple. And if you check this scale, the purple here shows that what it is, this is 1, and this is tending towards minus 1. Just like saying here, this is also very correlated to it, and this likewise, this also differential pressure minus 0.8 is also correlated because it's also pop is like 84%, minus 84%. That's highly correlated to, highly negatively correlated. So when we now do that, this particular feature is saying from sklearn.feature selection. From sklearn.feature selection, import select k-best f classic. So what we are basically doing here is saying select k-best and f classic. I'm just selecting features. You just, can you see, just like that, feature selection. So I'm doing this, selecting the 5 best features. I'm saying x is equals to, I'm selecting it based on this failure label, and then the df predictable. I'm using the log -1. This is just saying that the last value, the last integer -1. This is the last integer here, failure label. So just like that, I'm doing that. Then I'm getting my y. I'm saying clash. I'm just representing any parameter to, I'm representing it with any parameter here. Now I'm transforming this x and y. Now when I get my best features out, it's saying intake temperature, motor temperature, discharge pressure, to current, intake temperature are the best 5, 1, 2, 3, 4, 5. Best 5 that are highly correlated. Now if you take it, intake temperature, motor temperature, like I said, visually we can see that these are the highly correlated, and intake pressure, these are the highly, just like this. It's saying the best 5 are the best ones to predict the failure label. It's just, this feature is just to tell you the best 5 features that you can use to predict. Now basically saying, I'm not saying okay, these are the real, I represented this with real, saying real are the ones I will use to predict. Now I'm saying intake temperature, everything here, I just put it here. Now I'm not saying df real.8. Now this is what we use to predict. I'm not adding failure label to it. I've added failure label because we need failure label also to predict. So these are the stuff I will use to predict. Now I'm not training the data set. F is equals to df into square bracket real dot drop failure label, because our failure label is our, in prediction there are two things. There are the features and there's the target. The features are the independent factors. The target is the dependent. It depends on the features. Now this failure label, if all these are 0, then this will be, the failure will be yes, which is 1. But since all these are numbers, then the failure is 0, which is no. So it is depending on all these features, but all these features, they don't necessarily depend on it. So that's why we have F as features, T as target. I'm dropping this failure because I'm just doing, so that means this F is only this, and this. And you can see this is 1, 2, 3, 4, 5. 5 columns. And if you check the shape of it, 5. This is rows. Number of rows, it has 15,115 rows and 5 columns. Then the T shape is just 15,105, and then it's 1. You wouldn't put the 1 here, but we know it's just 1. Just T shape, just this failure label. That's why I say iLock is just this. This is just the code for it. Now from sklearn.model selection, import test train and grid search. So this train test split is just to split our data set into, I splitted data set. This is the test size. That means the train size will be, if the test size is 0.2, out of 1, we're taking our data set as a whole. Out of 1, we have the train size to be 0.8. So 0.8 to 0.2. Now F train shape, F test shape. I'm just, after splitting, this is just splitting to split our data set into 80% and 20%. Now F train and F test. F is our target. If I'm training F train and F test, that means F train is just 12,092. This is 80% and this is 20%. This is our test size because we are using F test. We are using F to train, then we are using F to test. So T train, likewise the T is also 12,002, then this one is also the test. Now we are getting to the prediction using neural networks. For neural network, we use something called TensorFlow. Now, just like I did in the very first block of code, I'm importing these libraries. I'm importing TensorFlow as TF. From Keras models, I'm importing Sequential. Sequential is a model used in artificial neural networks. Now, from Keras.callbacks, I'm importing model checkpoints. I will explain it better when we go on with the line of code. Now, I'm saying our model, I'm representing our model to sequential. This sequential here, I'm representing our model to be sequential. So instead of writing sequential, into brackets, does this, we have already represented with its model. So we don't need to struggle with that. So model.add, I'm now adding TensorFlow.keras.layers. The layers I'm using, like I explained in the Word document, I'm using dense. .layers.dense, unit is equals to 64. The unit I'm using, I'm using the input, this is the input layer. Its unit is 64. That's the number of neurons, 64 units, 64 neurons. We are using artificial neural network. The activation is ReLU. The activation is ReLU here. I'm now using this kernel regularizer. Regularizer is equals to tf.keras regularizer.l2 as 0.001. The input shape is the F train shape. The F trace shape is 12,092, 5 columns. I'm not putting it as 1. That means I'm just using the columns, the 5. 1 means 5. This is 0 and this is 1. So I'm using 1. That's the input layer. For the hidden layers, I have this hidden layer here as unit 32. It has 32 neurons. I have 2 hidden layers. This 32 activation is also ReLU. Regularizer is this. Then this is a dropout. I'm dropping 0.5% of data. We do this dropout because to mitigate noise in a data set. When you are predicting, now noise is saying your model will be, now for anything, this prediction we are trying to make here is basically to, if you make a prediction on something, is to be able to say, okay, what we are predicting here is that if we take this particular model now, if we test a data set that has this exact column, right, these columns, if we find a data set and we have these columns and it has these values, it will be able to predict the accuracy of our model. We will be able to predict to that accuracy our failure label. That's like testing the data. That's why they do model deployment. So basically, we are dropping out 0.5 because we want to minimize noise. And when you minimize noise, it's basically saying, if you minimize noise in a data set, what you just did is you have now said, okay, the model should just to learn. You know what our model is doing here is learning different patterns of the data set. It's not just memorizing the data set. There's a difference between, okay, memorize this chapter in a book, and now after you've memorized it, if it's just time to memorize, I can memorize it word for word. I may not truly know the pattern of the words or what it means. But when you now tell me understand this chapter, that's what it is. We are trying to make the model understand the patterns that we cannot see. The model is learning it, so we can be able to see it. It's going to learn on the data set. So when you memorize that kind of stuff, when the model is just memorizing, it's just going to memorizing. It can even give you 100% accuracy. Is when it memorizes, it's just that, okay, it has memorized. It has not truly learned. That means if you feed another data set to it, it will not predict very well. It can only predict very well on the data set that we are using to train. But when your data set has learned, it is able to predict based on new data sets. Since it has learned a particular pattern, it's able to use to also predict on another data set with the same pattern. But if it's just memorizing, it will not. Now, if we don't drop out 0.5% or 0.5 of the data set, half of the data set, it is just going to be memorizing because there will be lots of noise. That's why we need lot of data sets, because we are still going to drop out some. And we'll still go further. Now, this is another hidden layer. This, before we dropped out 0.5, now we put another hidden layer, which unit of 12. Still the same activation value. We have units 12 neurons, and the kernel regularizer is still here. And then the model data, this is the output. We are using sigmoid because the activation is sigmoid because it is a binary kind of data set. It's a binary data set. Now, this is where we are now compiling the model. We are compiling the model on Adam. The optimizer is Adam. We are using Adam. It's a function in Python. And then the loss is binary cost entropy because it's a binary data set. And the metrics we are using is accuracy. Now the checkpoint, just if you can remember, we imported the checkpoints from keras.callbars import model checkpoint. What we are doing there is checkpoint is just model checkpoint to monitor. We are using a valency loss. We'll get there. We are using this for valency loss. So this best monitor is equals to this, and save best only is this. That's what we are using checkpoint for callbacks to minimize errors also. Now model.fit. Now I'm not fitting. You know, we have splitted the data set into two. There is the train data set, the train data set, and then the test. Now we are not putting the two train. We are training on the features and on the targets. If you are training on the features and the targets, if you are to do that, you have to say, okay, training on the data set, the features. If you train on the features, which is the 80%, when you split the data, and then the target, which is the 20%, you are doing this in the essence of being able to predict, to make prediction. Now I'm fitting the trained data set, which is our features trained and then the target trained. I'm putting the batch size as 34, which is the standard, and I'm putting epoch as 150. It is running 150 epoch, and then validation split of 0.2. That means I'm further splitting the data set from 80 to 20. I'm not further splitting it. I'm getting a validation split of 0.2. It is well explained in the. I've also put this in the Word document I printed out. And callbacks is equal to checkpoints that were created there. This verbose simply means I don't want to see it loading 150 airports. So I put this verbose just to get the process. Now we've done this, and then we can now check for our test loss and the test accuracy. Now for the test loss here, model.evaluate f-test and t-test. Now model.evaluate f-test and t-test is simply saying, okay, we are trying to get the accuracy. Like I said, metrics is accuracy. Accuracy here is what? 0.9985. That means this model is as truly learned. It is be able to predict on our data set with 0.9985 accuracy. And then the loss is 0.001. The loss is minimal. So the test accuracy, I printed it out, the test loss is same thing. And then the tip-read is saying, okay, now this is our prediction. The tip-read is our prediction. It's saying we are now predicting based on the model. The model, we just use the trained data set for the model. We splitted it. Remember, we splitted the data set. Now we are predicting based on the model. The f-test, we are predicting based on f-test. We are using it to predict the target. It's now saying, okay, we are getting the t-test. We are separating the t-test. We have f-train, f-test, t-train, t-test. We are now separating the t-test. We are now saying, okay, what if we just have the f-test, the features alone? We don't have the target, which is the failure column. We have the other parameters. Can we predict, because we fitted this trained data set on our model? Can it now predict successfully the tip-read? Can it now predict based on the model if we just have the features that we don't have the target? Can it predict? Yes, it can. I rounded it up so we can get a better value. Now the tip-read, now this is the array. You see, this is 0, 1.0, 0, 1, 0, 1. This is just it. This is the tip-read. Now from sklearn.metrics, this metrics is used to check the metrics. So from metrics, we can have the classification report, the confusion matrix, and the how-to score. Now confusion matrix is simply this. We are comparing to now check the, obviously we have our t-test before. The t-test is from the data set. The tip-read is what we just predicted. We are now, the matrix is going to check, is the model evaluation is checking the predicted values to the test values. It's just to test, the way of testing the accuracy of our data set. If it has truly learned, not that it has memorized it. Now if we do that, putting confusion matrix, it has 4 values. There is the false negative, there is the false positive, there is the true negative, and there is the true positive. Now this is it. I will explain this. Now what we did here is we also used heat map. I use varieties also, annotation to be true, to put the annotations there. Now since I've done this, I put the title as this, the X label as actual value. It's like putting actual versus predicted. In this way, these are the actual values, 0s and 1 and 0 here. So if you have, I will explain the concept of a true negative. A true negative is when the actual value is true and the model also predicts true. If the actual value is true and it also predicts true, if it's a negative value and it predicts true, let's say it's a negative value of, maybe something is negative, and if the actual value says it's negative and the model, the predicted value also says it's negative, that's a true negative. A true positive is also the same logic. If the actual value is positive and then the predicted value is also positive, that's a true positive. But a false negative is when the model predicts, the actual value is positive and the model predicts negative. That means it is a false negative because that's not the actual value. The actual value is actually positive, but then it has predicted negative. That means it is a false negative. Likewise for false positive, if the model predicts, if the actual value is negative and the model predicts positive, that means it is a false positive. That's just basically it. So here he's saying 1 is saying yes, right? Our 1 is yes, our 0 is no. Now if this 1 and 0, that means the actual value here, which is 0, is 0, and then we have this one which is yes. This is no and this is yes. Now if this is no and this is yes, this is no here and this is yes here, we have 4. That means we have 4 no. No is a positive stuff, right? That means we have 4 false negatives. Because this is saying this is yes, this is false negative, because we have 4 false negatives. That's a fault on our model. That's the accuracy. That's where the accuracy comes in. But which is 0 and 0, that means we have this large number, which is 0 and 0. That means this is a what? True positive, because 0 is no. And no, when you have no for failure label, it is a positive. This is 1 and 1. Like saying here, 1 and 1. 1 and 1 is a true negative. For our false negative here, we have 0. For our false positive here, rather, we have 0, which is also good for our model. If you have 0 false positive, that means there are no false positive, but there are false negatives here. Just 4 negatives. That's very good. Now, when we do actual versus predicted, you see, the actual versus predicted is just basically plotting the actual value versus the predicted. This is just it. It is not a straight line, but it's just showing the relationship between our actual versus the predicted. Now the classification report, for the precision we have 1.0, 1.0 for 1, for 0 and 1, which is no and yes. 1.0 for the recall, 1.0 for the F score, and the support. This is the support. And then for the accuracy, we have 1.0, which is 100%. 100%. This means it is very good. The R2 score also is very, very close to 100%, which is 0.994. It is a very good metric to do this. So this is the end of the prediction and for ANN. I look forward to hearing a feedback on how we would go about this, and this has been very good. I hope you understand this. Thank you very much.